Atsushi Kurosawa is the Japanese delegate to the EGRD and also, together with me, one of the vice chairs. He is director at the Japanese Institute of Applied Energy. Thank you, Atsushi. The floor is yours.
Okay, thank you very much for the kind introduction. Can you hear me? Can you hear me now?
Yes, we can hear you.
Yep. Okay, second session is the, we have a full presentation from the distinct speakers focusing on the R&D needs and along the value chain of critical minerals for clean energy technologies. So this session focusing on the demand of critical minerals in terms of demand itself and also the efficient use and reuse and recycling and substitution. The second topic is the production and processing of critical minerals in terms of the unlocking new supplies like from the low-grade ore and so on. The third one is the circularity and environmental impacts and the social impacts. So maybe we have 1 hour for 4 speakers. So if you have a question from the audience, please write your question in the Q&A, please. So, okay, the first presenter is the Mark. How do you pronounce your name, Mark? Kozdras? Yes.
Kozdras.
Kozdras. He's an emeritus scientist at Natural Resources Canada. He is also the international co-lead of the Materials for Energy Collaboration, a platform of mission innovation, and NRC CAN representative in the design development team for the new Center for Accelerated Material Discovery and Innovation. Recently, he's retired. He plans to maintain his close ties with the Energy Innovation Committee for the foreseeable future. So, Mark, the floor is yours.
Thanks very much for the introduction. Again, it's Mark Kozdras from Natural Resources Canada. And the introduction that we had already is very inspiring. And I'm trying to do just a little bit of a job to show how across the supply chain, accelerated materials discovery is a very important aspect to move us forward into the future. We can see from the previous presentation, the role of critical minerals in clean energy transitions, that there's a lot of priority materials that we have to consider as we look at the renewable technologies, the alternative ways of using energy and producing energy. And this slide, the pictures in this slide come directly from a series of presentations that I've given for mission innovation for a long time. And they're very relevant to what we heard in the last presentation. The priority applications, renewables, we heard electric vehicles, storage, including battery storage, electrolyzers, fuel cells, they're all mentioned in the report. We heard as well the practical approaches. What are we going to do? We have to reduce the amount of critical minerals, reuse, replace, and enable. So find new ways of connecting those supply chains. And what's the rate of development that we need here? Well, it must be an accelerated development. What are the opportunities? Novel process technologies, improved refinement processes at the upstream, methods for recovery from waste. We heard about tailings. We heard about recycling. Metal recovery from dilute sources. And I'm going to talk a little bit about that during my presentation. Novel materials and devices. The other thing is, how do we use these? What's the demand side? What are the devices that we are making, and how do materials play a role? Increased localization of process systems. We often move materials, raw materials, long distances, and we saw that in some of the slides earlier. And it'd be good to have processes developed, efficient processes developed more locally, and possibly those will be enabled by substituting the materials that we typically ship. So what's the strategy that I'm presenting today? It's new technologies along the supply chain through accelerated materials discovery and development. And what I'm focusing on is autonomous or self-driving materials laboratories, something that is very much the center focus of my role in mission innovation and materials for energy. So what is a self-driving lab? It's basically a closed loop system where we take characterization and synthesis, so making a material and characterizing that material in situ. That's done robotically, which means that we can run experiments continuously, perhaps even 24/7. The way we drive this is through accelerated experimental planning and simulation and modeling. So we need high performance computing to drive ideas on where to go, and inverse design approaches that allow us to identify potential materials and use the synthesis and characterization, the robotic platform, to actually make those materials or attempt to make those materials and characterize them for the properties that we're looking for. And the idea here is to develop novel materials and/or right up to the full device. You can see on the right side, the Materials Acceleration Platform report. It was done in January of 2018. So we've had just around 4 years to develop this concept at the international level through international collaboration. And we've advanced fairly effectively. I'll talk about one example, an early example of material substitution. So if we're looking at organic photovoltaics, the work at Helmholtz Institute, Erlangen-Nuremberg is quite effective in showing how we can develop new materials to create organic solar cells. And these experiments that were done in the platform that you see on the left were able to show that they could do through both high throughput experimentation, but also through the AI robotic system that you see there, known as Amanda, that they could increase the rate and find solutions within 30 experiments to find a solution that was as effective as 1,022 experiments in using high throughput experimentation. And if we use conventional science methods, we would probably find that it takes much, much longer to be able to achieve the same goals. So accelerated materials discovery is enabling finding new materials that can replace one of those critical minerals, silicon in this case. Another example that was funded by Canada as a result of the Mission Innovation Initiative, and it's the University of British Columbia Project Data. Again, this one's focused on organic solar cells. So the platform that you see on the right, top right, is an example of how modular, how small the systems can be to do the development. This system was working on whole transport materials, one layer in an organic solar cell. On the bottom left, you'll see that the cycle time for a robotic execution of an experiment to synthesize 13 minutes, to characterize 7 minutes, and to plan the next experiment through artificial intelligence, machine learning. They're using 1 minute, less than 1 minute, to go and find the next experiment in the experimental space. One thing to note is that the experimental space can be extremely large, the number of factors that they're looking at any given time. And the way that they search it is quite effective in finding the best material in that experimental space. And you can see that they progress within, again, on the bottom right, they progress very quickly to a solution because they're searching the experimental space effectively and rapidly using robotics. Another example that's under development with partners of Natural Resources Canada, the National Research Council is developing electrocatalyst automated system, automated robotic platform. And the electrocatalysts will be important for electrolyzers, fuel cell type technologies, but also hydrogen production, CO2 conversion, and oxygen evolution reactions. So this platform is just nearing a point of operation at a lab local to my lab. And it's focusing now on mixed metal oxides. Again, many different metals are identified, but they're going to work on creating the electrocatalysts that will enable the types of reactions that we need moving forward. An example, in our lab, we're working on a high temperature map. So this robotic platform basically is able to take metals and metal powders, dispense them, melt them, and or heat treat them, and then analyze it. So we've got the synthesis portion of this automated platform functioning now. We're still working on the characterization side. And one of the places that we're working on using this is in the heat treatment of aluminum scandium alloys. And the scandium is used here to strengthen the aluminum, but not affect its electrical conductivity. And where this becomes important is we're going to use these materials as we develop them and move them into conductors for electric motors. This is the size of the platform for the synthesis of the materials that we're looking at right now. And so you can see it's very compact and robotically driven. Another area, and we talked about tailings and waste, but another area we're looking at is supporting some work that is being done by Standard Lithium, a technology, selective ion filtration technology, and developed by Telescope Innovations. And I just got permission to use those companies. But what we're doing here, what they're doing here, and what we're working with them on at NRCan is a concept to take brine solutions and extract lithium. And they've demonstrated at scale that they can do it at high yield and high purity as we speak. So we're now going to look at how we can generalize these to different brine solutions, but not only that, look at recycled batteries. And we heard about recycled batteries earlier. So there's many, many applications here. And I just wanted to kind of highlight the opportunities: silicon replacement, platinum group metal optimization and replacement for electrolyzers and fuel cells, copper replacement as through our aluminum scandium conductor work, lithium extraction, new techniques for that. And we've had discussions around things like mining flotation. So maps and accelerated material discovery can be applied to all of these. Thanks very much.
Thank you very much for your presentation. So we have 3 minutes. So I wait the questions from the floor. So if not, otherwise I have one question for you. So you have stressed on the productivity gains on the material informatics. So maybe you need a database for gathering the data and also the initial data. For usually we use a teacher's approach for the machine learning from the scratch. So which kind of strategy did you take?
It's interesting. Data and AI, the machine learning has been looked at very, very carefully. One example that I didn't put in was the Battery 2030 initiative in Europe and under Horizon 2020. And a large portion of the work that they're doing there is developing a battery interface genome acceleration platform. There's one large package of work that's looking at data ontologies and how to curate the data for one thing, and how to convert it into a language where machine learning can be applied. So that's one very large project that is focusing extremely closely on the data curation. Every one of our projects is learning from some of the work in that project, but developing those data curation methods and databases. So it's a thing that's very important in these types of platforms, and the work is only 4 years old, so we're going to be focusing on that a great deal.
Yeah. Potentially accumulation of data increase the productivity much more. I think it's very promising approach. I suppose. So another question from the floor. There's one question from the Bart Jorgensen, chair of EGRD. What is a floating mining?
The flotation actually is a process where they use bubbles to grab particles to bring them to the surface for a separation technique within mining. Now, I'm not the mining expert. I'm more about trying to understand how we can create a automated platform that will actually study the reactions and rapidly identify the parameters that work the best. So it's about mining, it's flotation of particles, ores, and materials for a separation technology.
Yes, it's very common technology in the separation jargon. So another question is from also the Butter. Do you get funding from industry for this important research in general?
Yeah, it's a good question. Berta probably knows that the early work, and again, we started the mission innovation activity 4 years ago, and we've done a fair bit with government funding focused at the beginning, but we are engaging many new partners. And there's an initiative at the University of Toronto that I'm involved in that is closely linked to industry and industry partners. And they are now funding, in a general sense, work in this area, as well as funding some of the projects that are going to take place to leverage the technology, the autonomous lab technology. So yes, we're starting to see that now.
Okay. I appreciate the opportunity. So thank you very much for your
Very good
presentation. So
thank you.
I'd like to move to the next presentation. Presentation from Michalis Christou. He's a senior expert in energy, security, and transport at the European Commission's Joint Research Center at Petten. A mechanical engineer trained with a PhD in risk analysis. He has worked on energy analysis, protection of energy and critical infrastructures, and security of energy supply and supply chains. With his team, he is performing research on the foresight of materials demand for the energy transition, the resilience of supply chains, and the mitigation of supply risks. So, Michalis, the floor is yours.
Yes, thank you very much. Yes, can you hear me? Yes.
Yes.
All right. Thank you very much. Thank you, Chair. Thanks also for the invitation to this very important webinar of EGRD. Allow me to share the screen. Yes.
Yes.
Okay.
You can see it. Go ahead.
Okay, perfect. So, good afternoon, good morning, good evening, colleagues. I'm Michalis Christou from the Joint Research Center, and we're going to discuss about similar issues as in the IEA report and the notes and the remarks of ministers. So about the green energy transition in the European Union and what material and supply chain challenges we have. Allow me just a minute. Okay. Allow me to spare one word about who we are. We are part of the European Commission. The Joint Research Center is the Directorate General of the European Commission, actually the in-house scientific body. And our mission is to support the European Union's policies with independent evidence throughout the whole policy cycle, from anticipation to development, implementation, and review of the policies. I'm from the Energy, Transport and Climate Directorate, and I'm located in one of the facilities of the Joint Research Center, which is in Petten in the Netherlands. So we will discuss exactly about the ambitions of the European Union to have a transition of the energy system towards climate neutrality by 2050, and also to reduce, to achieve a reduction of the greenhouse gas emissions by 2030, by 55% with respect to 1990. This is what we call the, and you are possibly aware of this, what we call the Fit for 55 pathways and objectives of the European Union. At the same time, there is the need to make our system independent from the, especially from the Russian fossil fuel. Especially after Russia's invasion of Ukraine, and therefore the European Commission has come with the Repower EU, a plan, an action to make more affordable, secure, and sustainable energy well before and independent from Russian fossil fuels by before 2030. Interestingly, at the same period, we had at the London Metal Exchange stocks market, it had to stop transactions when the price of battery grade nickel rocketed above $100,000 per ton, reminding us that these value chains, the supply chains, need also to be resilient. So this is what we are going to discuss now. First of all, for the Fit for 55, what would be the capacity requirements, especially for wind and for wind power and for solar PV? I'm going to present some results of some analysis that we have performed in support of the upcoming initiatives, and we are based here in one Fit for 55 scenario. This is a mixed scenario. So it is based on both on the carbon pricing, but also in a mix of exogenous regulatory measures, combined with the use of renewable, the production and the use of renewable hydrogen. The analysis that we will see and the scenarios analyzed here are prior to Russia's invasion of Ukraine. So as you see, for onshore wind power, there is a need for an increase about 2.5 times in this scenario, whereas for offshore wind capacity, the increase should be about 5 times. Similarly, for solar PV, we would have during this decade, a 4 times, a 3.5 times increase. So the main question is, do we have the materials and also in the quantities that are needed for this ambition? So materials and what quantities do we need for the Fit for 55 ambition. We have performed an analysis combining competencies and modeling expertise and tools, both from energy system modeling to analyze the necessary installation new deployment rates, also technology assessment in order to see what mix, what share of the different technologies would be, and material intensities information and knowledge. So the materials demand projection as a percentage of the current total EU consumption is presented here for the main rare earths, neodymium, praseodymium, dysprosium, and terbium. We see significant increase, around 4 times increase in the need of permanent magnets and the materials for wind turbines. The question is, do we have these materials and these components? So we have performed a supply chain analysis, a complete supply chain analysis of the complete value chain of wind power, of the wind turbines, from raw materials to processed and materials and components and assemblies. And we see that there is a strong dependence, there is significant concentration. China is the main supplier of permanent magnets for the globally, I would say, but also for the EU. And there is therefore a strong dependence on China. So coming now to solar PV, again, the forecast analysis for the material demand scenarios for this particular scenario. Of course, we have to distinguish between the different technologies, the crystalline silicon technologies, which count for 95% of the market, and the thin film technologies that count only 5% of the market. So we identify significant increase for silicon metal and silver, and for the thin film technologies of the critical materials, germanium, indium, gallium, but also tellurium and selenium. So there is significant increase in the need for solar PV cells and the materials for solar panels. Again, the supply chain analysis for solar PV identified that we have strong dependence on Chinese companies, especially large part of the PV cells and modules are imported in the EU by China. Okay, and we see that this persists also even to the assemblies. So what we have seen from this analysis that that Fit for 55 ambitions will bring a surge in demand for critical components and materials for wind power and solar PV. Possible actions to increase resilience of supply chains include, of course, the technology selection based, of course, on the availability of different technological solutions. Sometimes, for example, for onshore wind energy, because for offshore it's rather it's more difficult to replace the permanent magnets, and also for the technology of PV cells. Diversification, of course, of material supply, increasing the domestic manufacturing capacity of clean energy technologies components for certain components, enhancing recycling, reuse, and substitution, promoting, of course, RD&D, and I must say that in the previous and this year, about 300 million euros have been devoted to projects of critical raw materials through Horizon Europe. Something very important, promoting international cooperation and strategic partnerships. And indeed, we have in the EU strategic partnership with Canada, with Ukraine, and also we are planning other partnerships and international collaboration, and of course promoting responsible mining. I have seen the comments in the chat. That's something very, very important, and ensuring a level playing field. And of course, it is necessary to reflect and take the measures that taking the note that making Europe independent from the Russian fossil fuels well before 2030 requires acceleration, of course, of deployment of renewables. But the fact that many critical materials and components are sourced in China carries the risk of exchanging, one energy dependence with another. It's very simplistic what I say, but we need to take the measures to mitigate this risk. Before closing, I would like to remind the action plan on critical raw materials of the European Union that was in the critical raw materials communication of 2020. With first the establishment of the alliance, the European Raw Materials Alliance. You have seen development of sustainable financing criteria, various a list of 10 actions which are being carried out in order to address the issue of critical raw materials. Bring to the audience some relevant JRC reports that you can find in our repository. Especially this, the foresight study of the critical raw materials for strategic technologies and sectors, that we have looked at various sectors and various technologies and identified which are the relevant materials, what is the supply risk, and made this foresight study. This period we are extending this to 15 technologies in 5 sectors: energy, mobility, industry, digital, space and defense, with the demand forecast and supply risk for the complete value chain. And before closing, let me mention some examples of R&I activities, focusing especially on magnets, the one from ERMA and the EIT, which provides a kind of an overview, but also discuss and consider various alternative technologies for wind turbine generators, including the superconductor-based generator, the one from General Electric that I saw in the chat. There was a reference previously with ultra-low temperatures superconductors. The green spark generator, etc. Always, of course, we need to balance the gain in the quantities of raw materials used with the efficiency and the performance, and also some hints to some European R&I projects. So thank you very much. If there are any questions, I will be glad to answer either now or feel free to write to me. Thank you very much.
Okay, thank you very much for your excellent presentation. So I wait for the question to come. So before that, I would like to raise my question. So it is obvious that current rare earth supply governed by China. So we need to diversify the supply source. What is your thinking about the diversification.
Excuse me, I didn't hear you well.
What is the diverse supply other than China? So.
The diversification. Okay, most of it. Okay, we know that it comes 90% comes from China. There is still the rest 10%, let's say, that needs to be exploited. Also, yeah. Indeed, efforts should be done about different sources, so recycling and reuse, and there is an opportunity there because the very first generation of wind turbines are going now to the end of life, so there are opportunities. The problem, as you know, is always the difficulties that we have with recycling. Yeah.
Recycling. Yeah.
Right.
Okay.
Thank you.
Thank you very much. So time is up. So thank you very much for your presentation. I'd like to move the next speaker's presentation. So next speaker is the Diana Bauer. She's a acting deputy director of Advanced Manufacturing Office within the Office of Energy Efficiency and Renewable Energy at the U.S. Department of Energy. She is responsible for technical coordination and strategic planning, and also the departmental and interagency leadership in energy storage, critical materials, and the energy water nexus. She also belonged to the Office of Policy in the past and contributed to the 21 and 2011 critical materials strategy report issued by the DOE. So the floor is yours.
Thank you, Atsushi. Let me just share my slides here. All right, so I'm going to talk a little bit about the big picture strategy of DOE, and then do a bit of a deep dive into rare earths and kind of our work in rare earths. So let's get started here. Okay, so back in 2010 and 2011, we issued a critical materials strategy report that was based on or kind of adapted from a methodology developed by the National Academies. And we looked at materials or minerals under two dimensions, importance to clean energy and supply risk. And so back in 2011, we found a number of materials critical, including neodymium and dysprosium, which are used in magnets, which still, you know, as we've been hearing today, are still really important for this transition to the clean energy economy, and in fact are perhaps even more important than they were back in 2010 and 2011. In addition, we have kind of materials related to batteries, as well as some others on the chart. And right now, we DOE are in the middle of developing an update to this criticality assessment, and in which we'll look at some additional materials. So in general, and this is very consistent with what we've heard in the presentations shared thus far, our vision is for resilient, diverse, and sustainable domestic critical mineral and material supply chains to support this clean energy transition. and decarbonization economy-wide. And basically, we have 3 pillars for the strategy, and this is, a strategy to inform the research that we support in the department. First is diversifying supply, and this includes innovation in processing as well as, finding additional sources, developing substitutes. So this aligns with some of what we heard earlier, just in the last presentation about new technologies for wind turbines, for example, that don't require as much permanent magnet use. And then finally, reuse, recycling, and more efficient use. So this is both innovations that reduce the quantity of material required for certain functionality, and then also increasing recycling. And this is particularly important as we get to the end of life of technologies that we're entering, that are entering the market today. So as we're ramping up the use of these materials, right now there maybe isn't as much quantity available for recycling, but in coming years and decades there will be, and so we've got to get the recycling going now so that we'll be able to capitalize it as the materials become more available. So so now in the next slides, I'm going to focus on rare earths, and particularly rare earths used in magnets, just to give you a flavor of the department's sort of comprehensive approach to these, magnets and their supply chains. So first of all, last year there was a executive order issued in the U.S. on supply chains, and DOE completed a number of reports, including one on rare earth magnets. And so this America's Strategies to Secure Supply Chain for a Robust Clean Energy Transition had a report that looked at in depth at neodymium magnet supply chains, and described our research, development, and demonstration activities, as well as some recommendations for future work. So we have quite a bit of work spanning from fundamental to applied research, and we have also research from mining to recycling, so through the full supply chain. And we as a department are working to kind of accelerate commercialization and deployment through additional infrastructure investment. The department has a newly formed manufacturing and energy supply chains office that is focused on infrastructure and deployment. And then in addition, we have a new rare earth element demonstration facility that was mandated in the Infrastructure Act that passed last year, and that's a significant investment within that act. And other policy related work includes a critical mineral stockpile, bilateral and multilateral cooperation and collaboration, and then finally standards to promote supply chain transparency and traceability. So here's a figure from the report that I mentioned coming out of the supply chain executive order, and these findings are very consistent with what we've heard in some of the previous presentations in this section. for rare earths, you can see in the figure on the left that the distribution globally of mining, separations, refining, and magnet manufacturing for neodymium magnets. So you can see that while for mining, China still has more than 50% of the mining, they don't dominate as much as subsequent steps in the supply chain. So separations, actually there's production of rare earths through mines in the US that then gets shipped to China for separation. So you can see separations, refining, and magnet manufacturing. As we go further in this midstream supply chain steps, China dominates more and more. So on the right, you can see mining, extraction, concentration. The midstream separations, processing and refining, and magnet manufacturing are a vulnerability for the U.S. And for our allies as well. And then we do have manufacturing of technologies that use these magnets, such as electric vehicles and wind turbine generators. So as we ramp up, we definitely want to strengthen this midstream segment of the supply chain. So we also, there was a question earlier about diversification of supply of rare earths. As I mentioned, there's Mountain Pass mine, actually is an active rare earth mine, but it currently exports its concentrates to China for separations and processing. We also have another site, White Mesa Mill, that does produce some rare earths, but we have a number of other potential producers who are working on scaling up or developing commercialized production, and it's so we have the potential for quite a bit of diversification of production. So on the next several slides, I'm going to talk some about different offices within DOE and kind of their role in this overall picture of advancing the research to support addressing vulnerabilities and improving resilience in the supply chain. So the Office of Science is responsible for fundamental research, basic research related to critical materials, and this includes understanding the role of rare earths and platinum groups and other critical elements in energy technologies and characterizing the properties and designing new materials that use these elements. They're also very active in separation science, fundamental separation science, to help inform environmentally friendlier separations, more energy efficient separations, and also they support fundamental understanding, improvements in fundamental understanding in order to get us more efficient atom by atom of using these materials. So the Advanced Manufacturing Office, where I reside, has a fairly robust portfolio of critical materials and minerals work across the full life cycle. We have this portfolio of work that's aligned with the strategy to, again, diversify supply chains, develop substitutes, drive reuse recycling. And then we have R&D projects in these areas. We have the Critical Materials Institute, which has been around for about 10 years and is focused on, again, diversifying supply, developing substitutes, and cross-cutting research. And it has driven a lot of work that is sort of poised for commercialization. So we actually want to encourage scale up of this work, this sort of earlier stage TRL into mid and later stage TRL. And then we have separations across the supply chain within the Critical Materials Institute. So benefaction, efficient leaching, transformational processing, and then also separations at the recycling stage. In the Office of Fossil Energy and Carbon Management, we have quite a bit of work looking at unconventional and secondary sources across the country, often related to coal feedstocks, coal-based feedstocks. And then in ARPA-E, we have work related to bio-based processes for next generation mining. And we have quite a number of projects that have been kicked off in 2021. And that's the end of my presentation. Thank you very much.
Thank you very much for Diana. So there's one specific question from Bate. So what is the annual public R&D investment in the critical materials in the budget scale?
Yeah, so in the last number of years across the department, it has been between $100 and $200 million. And in the bipartisan infrastructure law, that potentially at least doubles that investment.
Okay, so I understand this bipartisan support is very
yeah
helps your office, I suppose.
Mm-hmm.
Okay. So the time is up. So I'd like to move to the next presentation. Thank you very much for Diana for the excellent presentation. So next speaker is the Chiharu Tokoro. She is the professor at the Faculty of Science and Engineering, Waseda University. Her research focuses on mineral processing, chemical engineering, and powder processing and waste treatment and recycling, especially for advanced separation technology. She holds many non-executive positions, including outside director of JEX, Nippon Mining and Metals, a member of the third section of the Science Council of Japan, and several Japanese government councils. Tokoro Sensei, the floor is yours.
Thank you very much, Kurosawa Sensei. So let's start my presentation. So thank you for inviting me to present my research works. And today's my topic is separation, especially for the pre-treatment detachment before hydrometallurgy or pyrometallurgy for critical metals, including base metals for lithium-ion batteries or photovoltaic PV panels or multi-materials. So time is limited, but I want to show the concept of my research works. So this figure is very similar to the circular economy butterfly map proposed by Aaron MacArthur. And so we need diversity of the reuse and recycling like this, and also to support them, we need a very free, selective separation, flexible, selective separation and decomposition control at the interface. So in the current situation, we already have the near processing or recycling technologies, physical separation like a flotation, and also chemical separation like a pyrometallurgy or hydrometallurgy or some electrical one and something. But we need more selective separation directly at the interface for the reuse or repairing something and functional value use like this. So we are trying to sum up these kind of technologies. So this is one of the example of the metal circulation. So in the current situation, we have a very, very long with big circulation like this. And actually, this circulation is very important to support the recycling, elemental recycling of more high value, economical high valued metals, but actually in several materials is wasted to the final disposal. So we need more and more internal circulation like this to use more function of materials like glass or some low economical value metals or plastics or something. So we are trying to create this internal loop like this. And actually we have not so good separation technologies in associating. We have two kinds of separation technology like shredding or hand dismantling, but from now on we need more and more smart and selective and automated separation technology like this. And one of the example is more smart grinding, more smart shredding like this. So shredding is very common for the detachment or pretreatment at the first stage of the recycling. But we think we can use this kind of shredding more and more smart style to understand the mechanism of the grinding or impact compression or impact or shear or friction like this. This is one of the example of the more smart separation for the Sterafont. So we use this kind of drum type separating machine, and we can separate, we can achieve the liberation, high accurate liberation of the printed circuit board or lithium-ion batteries from the spent product like this. And also this technology can be used for the detachment of the parts. Several parts used some special critical metals or rare earths, for example, tantalum or something, and we can separate the printed these parts from the printed circuit board. But now we are trying another concept of the external forces to liberation, the electrical disintegration. We use high voltage application, and in this technology we can conduct the streamer propagation and generation of shock wave and micro explosion at the interface occurred by electron avalanches, and the shock wave can be separate at the interface between the product. And when we apply this kind of electrical disintegration in water, for example, in a printed circuit board, we can get another separation, another selective separation to shredding like this. For example, each parts can be separated between the resin and the metal parts due to the electrical disintegration. But now we are now trying more accurate electrical disintegration for lithium-ion battery or PV panels or merged materials like this. And this is one of the examples of separation of lithium-ion batteries, separation between the aluminum foil and the positive electrical particles mainly consisted of the cobalt and nickel, the manganese and lithium. And this is a video to show the accurate separation between aluminum foil and black mass. Black mass means positive electron particles mainly consist of cobalt and nickels. This technology applied in air, but we can also use water, and just one of the electrical disintegration, we can clearly separate between the aluminum foil and the black mass. And the aluminum foil is very clean, and we hope we can recycle this aluminum foil, and also this black mass remains a function as positive electrical particles, electrode particles. And now several companies in Japan try to direct recycling of this black mass to the lithium-ion batteries. Okay, so this is one of the examples of the direct recycling. Of course, we have many issues to achieve this kind of technology, but this is just the beginning of the technological development. But I hope we can create a more internal reuse or recycling loop by this kind of separation technologies. And also we evaluate the LCA for this kind of technologies. Time is limited, but I just show you that this kind of separation is very good in the scope of the LCA. And also, this kind of electrical disintegration can be applied to the selective metal recovery inside from the resins. So metal explosion, plasma conversion can be occurred for the, for example, the metal in the resins in the PV panels, and we can separate directly just for the metals from the inside of the resin like this. This is a video of the separation by using the electrical disintegration to separate the metals inside of the resins. And also we can try this kind of separation to the adhesive. Adhesive is mainly used for the automobile or something nowadays, but we need to develop the new separation technology for the merged materials adhesive. And we also try to separate the adhesives like this. And when we can induce inside of the adhesive of high voltage application and the electric breakdown of adhesive inside of the adhesive, we can clearly separate between the merged materials like this. Okay, so this is summary of my presentation. There are many kinds of separation technology, but the key issue should be the selective separation at the interface, and now we are trying to achieve it. Thank you very much.
Thank you very much for Tokoro Sensei. There's no questions from the floor. Okay, so there's one from Bauer, chair of the EGRD. Do you collaborate internationally in this topic of field?
Unfortunately, we have a national project in Japan and also many kinds of cooperation in a Japanese company now. But we, of course, exchange information, but unfortunately, there is no cooperation internationally. It's very welcome for us. Thank you.
Thank you very much. So I think that your electric disintegration technology is very excellent and very high selectivity, I suppose. So the key of this technology is how to control the voltage and current in the wave form in your presentation material. So is there any optimality condition, or the do you have your research, especially for this kind of control technology?
Yeah, that's right. It's very important things to how to control the current and voltage inside of the each product, and so it's dependent on the each product. So it's very hard for us to optimize very adequate, most adequate conditions for each product. So we hope in the future, so we can design this kind of each product by separating by this kind of electrical disintegration. For example, the thickness or width or shape of metal inside can be common. It's very very good for our separation. We hope that.
Okay. There's a research frontier remains. So please have a good work in the future. Thank you very much for your presentation.
Thank you very much.